This is Physics 1020 and 1090. It's the lecture for Friday, April 3rd, and we're in starting chapter 28 on atomic physics. And in this first video for the day, I want to talk about Rutherford scattering. Ernest Rutherford is one of those 8 scientists I said you needed to know about, and he's one of my favorites. He was an English scientist, although technically he was born in New Zealand, but then he moved to England, was educated there, and did some of his greatest work there. He had a lot of contributions to science. He studied radioactivity, and he's also studied nuclear physics, and those are topics we're going to talk about in the next chapter, in chapter 29. So we'll see him again. But he also studied the nuclear structure of the atom. So he was able to figure out that the atom consists of a heavy nucleus with electrons going around it. Another thing I like about Ernest Rutherford is he's actually one of my, I'm a descendant of him academically. That is, my PhD advisor, John Wixrow, had a PhD advisor, William Fairbank, who had a PhD advisor, and you keep going back and back like that for about 8 generations, and you eventually find that his PhD advisor was Ernest Rutherford. So I've like to think that I follow in the Ernest Rutherford tradition. I consider Ernest Rutherford to vie with Michael Faraday for the title of best experimental physicist ever. Newton may have been the better physicist, but as far as an experimental physicist, I can't think of 2 better than Faraday and Rutherford. It's really hard to choose which is the best. This is one of his most famous experiments of Rutherford scattering. So, first of all, we start off with some alpha particles. Now, we haven't talked about nuclear physics yet, so I can't tell you exactly what an alpha particle is, but it's basically the helium of a nucleus atom. So it's 2 protons and 2 neutrons together form an alpha particle. And these, you can find radioactive materials that will shoot out alpha particles. And you, for instance, you can find some that will shoot them out at about 5 MeV energy, mega electron volt energy alpha particles. And you fired these alpha particles at this foil of gold, a gold foil, thin gold foil, kind of like the aluminum foil that you have in your house, but made out of gold. And the alpha particles would shoot through the foil and get deflected or scattered at some angle theta. Now, how would Rutherford detect these alpha particles? Well, it turns out when an alpha particle hits a zinc sulfide screen, it gives off a little flash of light. So you can actually detect individual alpha particles by watching for these little flashes of light. They're kind of faint. You have to watch carefully. So what Rutherford basically did is he watched through a microscope a zinc sulfide screen in a dark room waiting to see little flashes of light. So imagine what this experiment really consists of. It consists of 2 people in a dark room. One holds a stopwatch and tells Rutherford when to start and stop counting. And the other one looks through a microscope at a little zinc sulfide screen and keeps track of when there's a little light flash. And that's the way you get a Nobel Prize. So, what did Rutherford see in these scattering experiments? Well, before we can say that, we have to go back and talk a little bit about what people thought the structure of an atom was before Rutherford's time. And there's something called a plum pudding model, and this was promoted by one of Rutherford's mentors, J.J. Thomson, who was somewhat older than Rutherford. He said the atom was like a uniform positive charge, a large uniform positive charge with these electrons, which people knew were small discrete particles. Electrons it kind of put in at various spots. So you put that together, and the atom looks like a uniform positive charge with little electrons. He called it like a plum pudding. Maybe that's an English thing. I'd think of it more like a piece of raisin bread or something, where you had a dough that's kind of uniform with a couple little spotted raisins throughout. Now, you could take this plum pudding model, you could predict how alpha particles would be scattered by this atom. And if you do that, you find that you predict very small angles of at most a few degrees for the scattering of alpha particles. So the plum pudding model predicts small angles, and you can test that by going in and do Rutherford scattering. And that's what he did. Well, here's what he saw. He saw a lot of particles went through small angles, but he saw some of them were scattered almost backwards. In fact, he had one of his students by the name of Marsden look specifically for backscattering, for these very large angle scattering events where you send in the alpha particle this way and it bounces back and you detect it. So he found that sometimes the alpha particles were scattered back. What I'd like to do is I'd go back to our book, The Making of the Atomic Bomb, and read to you a little bit about Rutherford's reaction to finding out that these alpha particles could backscatter. Remember, so Marsden is Rutherford's student who did the initial experiment. Rutherford was genuinely astonished by Marsden's results. It was quite the most incredible event that has ever happened to me in my life, he said later. It was almost as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that this scattering backwards must be result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greatest part of the mass of the atom was concentrated in a minute nucleus. So, Rutherford's scattering basically showed that there had to be a nuclear structure to the atom. So Rutherford came up with his own model for scattering, and this is the Rutherford model. He basically assumed the alpha particle was a point charge with charge 2e. E is the charge of a proton, so this would be 2 protons, 2 neutrons. And he said, here's the nucleus of the atom, which is going to be very small, heavily massive, so massive that it's essentially stationary, and it has a charge plus z times z. That is, there's z protons. Z is the atomic number, and the atomic number tells you how many protons are in the nucleus. So you assume that there's z protons, so it's a large charge as well as a large mass in the nucleus. You fire the alpha particle, and the alpha particle is now going to undergo electrostatic repulsion. This is just repulsion due to electrostatics, like we studied the very first week of class. Like charges repel, so that the alpha particle would bend and would fly off at an angle theta because of this scattering event. So electrostatic repulsion, Coulomb's law, is something that's well understood, and Rutherford was actually able to solve and figure out how many atoms would be repelled at what different angles. And he was able to do this just by solving by Coulomb's law. So this is what he found for his scattering formula. Rutherford's scattering formula is here. It's one of these formulas we're not going to derive, but I wanted you to see it. It's got 1 over 4 pi epsilon naught. That's the Coulomb constant, K, in Coulomb's electrostatic law, force law, squared. It's got the atomic number z, the charge of the proton. It's got the kinetic energy of the alpha particle. And it's got this factor here, which depends on the angle theta. Sine to the 4th of theta over 2. So when you have a complicated equation like this, what you want to do is get some idea intuitively how it behaves. So let's look at some special particular angles theta. First of all, the backscattering. That's the one that Rutherford found so fascinating. Assume that the alpha particle backscatters. So it comes in, stops, and turns around and comes straight back. Well, theta is 180. 180 divided by 2 is 90. The sine of 90 is 1. So this whole factor here just becomes 1. And you get the Coulomb factor, which I forgot the squared. You get the 2ze squared over 4ke quantity squared. Just that factor that was out in front is how many are scattered at that angle, 180. If you look at 90, you get more, because 90 divided by 2 is 45. Sine of 45 is 1 over the square root of 2. And when you take the 4th power of 1 over the square root of 2, you get 4. So there you have a factor of 4. There's 4 times as many get scattered at 90 degrees than get backscattered. Now, one odd thing about this formula is if you put in theta equals to 0, you get sine of 0, which is 0. You get 1 over 0, or you get infinity. You get infinite number of particles scattering at 0 degrees. The reason why that appears is because when you have, Rutherford represented his nucleus as having a charge Z times E, and he ignored any electrons rotating around it. He assumed that the alpha particle was so close to the nucleus that you could ignore all these electrons orbiting around. But if you get a longer distance away, so it's going to scatter at a smaller angle, you can't really ignore the electrons. The electrons would shield the charge, so you wouldn't see the full nuclear charge because the electrons would cancel it out. And then this, if you take that into account, this factor of n at 0 degrees doesn't actually go off to infinity. But it is big, so most of the alpha particles didn't scatter much, but a few did scatter by large angles. Notice one thing that's not in Rutherford's scattering formula. There's no Planck's constant. Planck's constant was a hallmark of something that was quantum mechanical. Now, Rutherford, he wasn't really against quantum mechanics like Einstein was for philosophical reasons. He was didn't like quantum mechanics because he was a experimentalist. He liked to go in and do his experiments in the lab, and this fancy, newfangled quantum mechanics just wasn't his thing. So he was delighted that he could develop this formula without Planck's constant. However, if you solve this problem using quantum mechanics and Schrodinger's equation, you'll find that you get the same scattering formula. All the factors of Planck's constant cancel out. So it was really amazing that Rutherford was able to analyze an atomic system using classical ideas and get an equation without Planck's constant, and yet it was still valid if you looked at it truly in a quantum mechanical way. All right, so you can do experiments and you can verify that under almost all conditions, Rutherford's scattering formula works, and that was really good evidence for the nuclear structure for the atom. But you can also look at deviations from Rutherford's scattering formula, and you can turn to something about the size of the atom. For instance, let's look at the case of backscattered alpha particles. They come in, they slow down because there's this electrostatic repulsion, they stop, and then they turn around and they go back out. This is just like throwing something up in the sky. It goes up to the top, stops, and then comes back. Okay, when you're a long ways away, the alpha particle has all kinetic energy. But when you get in close, it has all potential energy. And this is the electrostatic potential energy. So remember, this is the Coulomb's constant, K. This is the charge of the nucleus, Z times the charge of the alpha particle, 2 times Z, over the distance. Remember, Coulomb's law says the force is 1 over d squared, but the potential energy is 1 over d. Now, so you can set these, just like you solve a problem in gravity, you can set the kinetic energy initially to the potential energy at the point of closest approach, and you can set those equal by conservation of energy, and then you can solve for the distance of closest approach. And this is what you get, Coulomb's constant, Z2 E squared over the kinetic energy. And now, that should work fine as long as the only force involved is electrostatics. But if the particle gets too close and it gets in here, actually reaches inside the nucleus, there's other forces involved. There are nuclear forces that hold the nucleus together. So what Rutherford could do is he could look at a lot of scattering and he could find what times that his scattering formula is valid and when his scattering formula would just begin to break down. And what he really needed is he needed small atomic numbers so that D would get small and it'd enter the nucleus. And he needed large kinetic energy, so he needed very energetic alpha particles. Again, so D would get small and it could get inside the nucleus. So he found that he had deviations from his scattering formula when he had a kinetic energy of about 5 MeV, which is 8 times 10 to the minus 13 joules. He used a low atomic number, Z of 13. That's aluminum. So he used aluminum foil instead of gold foil so he could get those alpha particles even closer and they could begin to interact with the nucleus. E in this formula is the charge of the proton, 1.6 times 10 to the minus 19. And this is Coulomb's constant, which was 9 times 10 to the 9th. Put those all in here, and what do you get? You get 7.5 times 10 to the minus 15 meters. Or in other words, 7.5 femtometers. Femto is 10 to the minus 15. Sometimes we call a femtometer a Fermi, just like 10 to the minus 6 is sometimes called a micron, 10 to the minus 15 is sometimes called a Fermi. So he's found the size of the nucleus, the radius of the nucleus basically, as 7.5 Fermis. That's really small. Remember, the size of an atom is on the order of a tenth of a nanometer, which would be 10 to the minus 10. This is up there around 10 to the minus 14. So the size of the nucleus is 10,000 times smaller than the size of the atom. It really is a large, massive, small in size, but massive in mass, a central spot at the center of the atom. So Rutherford not only was able to show that the atom had a nuclear structure, but he was able to say something about the size of that nucleus. So that is the story of Ernest Rutherford and his scattering, one of the key experiments really all in the history of physics. Next class, we're going to look at another property of atoms, and that is their spectra of light that they give off.